In this lesson today, I will discuss your homework about the problems about sound production. Number one, the more problems questions. A string of length 80 centimeters and mass of 16 grams is vibrated at tension of 800 newtons. What is the frequency of the second harmonic? The second harmonic note is equal to the first overtone. So here we need to use this equation F1 equals V over L. So first we have to find the value of the speed of sound. It is equal to the square root of F over mu, which is mass over L. And remember that mass should be in kilogram and L should be in meter. And we use F in Newton, so that we have V, which will be equal to 800 over 1 over 50. Then it is equal to the square root of 40,000 equals 200 meter per second. So F1 can be calculated as 200, the V, divided by the length in meter. So it is equal to 2000 over 8 or 250 hertz. Number two, a string of mass 0.2 grams and length 80 centimeter is vibrated at frequency of 250 hertz. What is the tension of the string that should be given so that 4 antinodes can be formed along the string? So along the string, which is 80 centimeters, we want to have 4 antinodes. I have drawn this for you. We have 1, 2, 3, 4 antinodes. So it will be 2 lambdas equals 80 centimeters. So the lambda will be 40 centimeter. And we know that V equals lambda multiplied by F. So we can calculate the V, 10,000 in the unit of centimeter per second. So it is equal to 100 meter per second. So if we want to find the tension, we use this equation. V equals the square root of F over M over L or mu. The V is 100. The mass is 0.2 divided by 1000. And the length should be in meter. So we have F, which is equal to 20 over 8 or 2.5 newtons. Number three, a copper wire of given density of length 2 meters and cross-section area 10 to the minus 6 meters squared is given a force of 360 Newton. And when the string is vibrated, calculate the frequency of the second harmonic. Frequency of the second harmonic is equal to F2. So we can use this equation because we are given the rho. We use V equals the square root of F over rho times A. dF is 360. The rho is 9 times 10 to the 3. And A is 10 to the minus 6 meters squared. So V is the square root of 40,000 or equals 200 meter per second. And F2 can be given by V over L for a vibrating string. So it is equal to 200 over 2 and it will produce 100 hertz. Number four, an open end tube A and a closed end tube B are of the same length, LA equals LB. Calculate the ratio between the first harmonic produced by tube A and the second harmonic or the first overtone produced by tube B. So we want to find F0A, the fundamental note of A, divided by the first overtone of B. FO of the open end tube will be given by V over 2L. And for the closed end tube, F1 will be given by 3V over 4L. So V is the same because it is the speed of sound in air. L is the same. Yeah, so we can cross them and we get a half divided by 3 over 4. It will be equal to a half multiplied by 4 over 3. It will be 2 to 3, the ratio. Number 5. The wavelength of the second harmonic produced by an open end tube is P, and that produced by a closed end tube is Q. So we have open end tube, the second harmonic, lambda 1 equals P, closed end tube, lambda 1 equals Q. Both tubes are of the same length, L. We want to calculate those wavelengths. P over Q. P over Q is lambda, the first overtone, lambda of the first overtone of the open end, and Q is the lambda of the first overtone of the closed end. It is equal to phi over F1 open end divided by phi over F1 closed end. So because we know that lambda phi is the same, so P over Q is equal to F1 of the closed end divided by F1 of the open end. For the closed end, F1 will be given by 3 phi over 4L, and for the open end, F1 will be phi over L. So we have the value of 3 over 4. For the multiple choice questions, we start from number 3. Your homework starts from number 3. When the tension of a string becomes 4 times larger, the frequency of the note will be how many times higher or lower? In this case, we use the equation of F equals the square root of tension over mu. So frequency is proportional to the square root of F. So if F2 equals 4 times F1, then frequency 1 over frequency 2 will be the square root of F1 over F2. We substitute F2 using this value for F1. So F1 over F2 equals a half. Then F2 will be twice F1. It will be higher. So the answer is, this should be C. We start from B, B, C, D. So this is the answer, twice higher. Number 4. In a closed end air column, air is blown so that second overtone is produced. Closed end, second overtone is F2. Along the air column, there will be how many notes and antinodes? I prefer to draw this instead of memorizing the formula. So in a closed end air column, there will be a node in one end and antinode in the other end. And there will be 5 over 4 lambdas when we have the second overtone. So we have 1, 2, 3 nodes and 1, 2, 3 antinodes. So the answer will be E. Number 5, the length of a string is 0.8 meters. The tension is set to produce wave of speed 400 meters per second. We want to find the fundamental frequency. The fundamental frequency F0 is phi over 2L. So the length is 0.8 meters. Phi is given 400 meters per second. So F0 will be 400 divided by 2 times 0.8. It is equal to 250 hertz. The answer is D. Number 6, the pitch of a note depends on, of course, this is frequency because amplitude, it will affect the loudness of a sound. Given the speed of sound in air is 340 meters per second, an open air column of length 25 centimeter will produce fundamental frequency and the first overtone, how many hertz? We want to find F0 and F1. F0 is given by phi over 2L. Phi is 340 and the L is 0.25 in meters. So we have F0, 680 hertz. And F1, of course, will be twice F0. It will be 1360 hertz. Or you can also use this equation. It will give us the same answer. So the answer is C. Number 8, the mass of a guitar string of length 1 meter is 2 grams and the tension is 180 newtons. When it vibrates, the speed of sound wave produced, we want to find V, which is equal to the square root of F over M over L. Just calculate, F is 180. The mass should be in kilograms, so it is 2 over 1,000 divided by L, 1 meter. So V is the square root of 90,000. It is equal to 300 meters per second. The answer is D. Number 9. A string is vibrating and the first harmonic is produced. How many notes are there along the string? So I draw this. For a vibrating string, of course, at the ends of the strings, of the string, we have nodes. So we have two nodes here when the first harmonic is produced. First harmonic is the same as the fundamental note. So the answer is two nodes. It will be B. The last one, the speed of a wave on a string is, we want to find the relation of the speed to the tension and other quantities. We can use this equation to find the first statement. V equals the square root of F over M over L. It is proportional to the square root of the tension, proportional to the square root of F. So it is correct. Inversely proportional to the square root of the density of the string. We use this equation. M over L is equal to rho times A, as I have explained to you before. So it is inversely proportional to the square root of the density. It is also correct. Proportional to the length of the string? Of course not, because phi is proportional to the square root of the length of the string. So it is incorrect. Inversely proportional to the length of the string? It is also incorrect. So the answer is 1 and 2. The correct statements are 1 and 2. The answer is A. Okay, so that's all. If you don't understand anything, you can, if you have any questions, you can always contact me in this number.